So let's begin again, please. I mentioned this last week, but I forgot to mention at the beginning of the day, I have an unavoidable meeting that I have to go back to Santa Cruz for in this afternoon. So this next session will be our last one today. We'll go from 1:30 to about 2:20 or 2:25, and then I have to dash for the car and drive back for a 3:30 meeting. So, and then next week, because there was no room available anywhere in Google for an all-day session, we won't be meeting at all. So we'll have a bit of a hiatus during which you can please send me any email questions you have about working on the problem sets, for instance, or beginning to read over the material and having questions. I'd be very happy to get back to you. I do get a lot of emails, so please put something like eBay Google short course in the subject line, and I'll try to respond with high priority to those messages. So we're here on about page 44 of the part 2 of the organized lecture notes. And I'm saying here, this is the thing that we noticed right before the break, which is that you can think of the prior in a conjugate setting as like a data set. That always works with conjugate priors. Even with non-conjugate priors, it's still a good heuristic to think of the prior as equivalent to a data set that can be merged with the sample data and then a likelihood style analysis done on the merged data. But without the conjugacy story, it can be hard to specify exactly what that prior data set is. So that's the difference between conjugate and non-conjugate stories. But the heuristic is a good one in all Bayesian work. So here's our updating rule based upon the conjugate beta prior. If your prior information can be captured with a member of the beta family with parameters alpha and beta, and then conditional on theta being a draw from that particular prior, you have the yi's given theta conditioned at IID Bernoulli theta as I runs from 1 to n. Then the posterior for theta given y is another member of the beta family, and the updating rule is simple. As I said before, alpha in the prior updates to alpha plus s, beta updates to beta minus s, beta plus n minus s, where little y is the vector of the actual n observables, and s is the sum. And so I mentioned before that it's very helpful to make a plot on the same scale, density normalize the likelihood, and make a plot on the same scale of the prior and the likelihood and the posterior. And so I've done that here. There's no point in drawing the picture all the way from 0 to 1 because the interesting action occurs from 0 to 0.4. If I had not labeled those three curves, how would you have known which was which? How would you have known that the lower curve is the prior? Just from the context of the problem, the way you have heard it laid out. Well, that's right. So that's one way. We know that the posterior and the likelihood should be close, so they should be the other two curves. So by subtraction, that must be the prior. But the other thing to say is that were we putting in a prior that had a high information content or relatively low or in between? Fairly low. And a low information content means what? A prior that's highly concentrated or a prior that's rather diffuse? That's right. And so the prior has to be the most spread out of the three curves. And then how can you tell which is the posterior and which is the likelihood if they weren't labeled? The posterior what? The posterior is a little bit to the left of the likelihood, and that's consistent with the idea of the posterior mean being a weighted average of the prior mean and the likelihood mean. Basically what's happening is that the prior shifts the likelihood story a little bit back toward the prior. That makes the posterior centered a little bit to the left of the likelihood. And what's the other thing in comparing the two of them that tells you which is which? Which curve is a little higher than the other curve? What's that? What I was getting at was that, as you say, the posterior is a little bit more concentrated than the likelihood because it's based on 430 pieces of information, and the likelihood is only based on 400, and the prior was based on 30. So you can tell it's the most peaked distribution here, the one with the smallest variability. It has to go a little higher, therefore, and all those other reasons. We could have worked out what those curves were without my having labeled them. So here we see graphically that in a situation where the prior had moderate information content but not overwhelming, with 40 observations in the prior and rather 30 observations in the prior and 400 in the data, the posterior is driven largely by the likelihood information. And as I've shown down here at the bottom of page 46, you can, in conjugate situations, write the posterior mean on some scale or other. It doesn't always have to be on the scale of the data. It could be on some reciprocal or other transform scale, but there is some scale on which the posterior mean can always be written down as a weighted average of the prior mean and the data mean, where the prior weight is the proportion of the total sample size in the posterior, here alpha plus beta plus n, that comes from the prior alpha plus beta, and the amount of weight on the data is 1 minus that, the proportion of the data, the total in the information in the posterior that comes from the data, namely n over alpha plus beta plus n. And you see the prior weight is about 7% here, and so one way to say what's going on is that the data mean of 0.18 has been, I'm not sure what the right English is for this. The idea is something called a shrinkage estimator. Is this the right English? The prior mean, rather the data mean 0.18 has been shrunken slightly toward the prior mean. Is that the right English? But anyway, that's the idea. We take the 0.18 and we shift it a little bit toward the prior mean, namely 7% of the way toward the prior mean, and that produces an answer of 0.178, which is not very far from the 0.18 that came from the data. So basically what we're getting here is that in this problem, for that particular prior information base, the likelihood answer and the Bayesian answer have tended to be similar, and that could give you rise to an objection on your part of the form, why did we have to go through all this Bayes stuff with all this stuff about beta distributions and blah when we just get the same answer anyway to what you would have gotten from the likelihood analysis? And the basic answer to that question is as follows. You don't always get the same answer. And when they don't agree with each other, there's a possibility for one of them to be better than the other one. And it's important for us to figure out under what conditions one of them does produce a better answer than the other one. The second thing to say is that we are now beginning to get a sense of possible situations in which the two methods do lead to similar answers. And that being the case, once we have a good handle on when that happens, we can use the likelihood analysis as an approximate Bayes analysis. And the great thing about the likelihood analysis, as we saw last week, is that it doesn't involve any integration at all. It's all based upon first and second derivatives of the log likelihood function. And so when the likelihood analysis produces answers that are similar to the Bayesian answers, then why not go ahead and use the likelihood analysis as an approximate Bayes analysis? So what are the features of this problem that have led to the likelihood analysis being similar to the Bayesian analysis? That's like asking, what was it about this problem that made the likelihood and the posterior so close to each other? And actually, there's two parts to it. One is that the prior is pretty flat, which is like saying the prior information content is relatively small in relation to the data information. But the other thing that's going on is that the other condition that gives you approximate equivalence of the two methods is when the likelihood and the posterior are both close to Gaussian, are both close to normal. And that, in turn, will happen when, by a Bayesian version of the central limit theorem, when the sample size is large. And so basically, the criteria for getting more or less the same answer between the Bayesian approach and the likelihood approach is when the amount of prior information is modest relative to the data information and when the data sample size is relatively large. If those two things are true, then the Bayes analysis is going to give you similar answers to the likelihood analysis. And you might as well save some effort and go ahead directly to things like maximum likelihood and get answers that are decent approximate Bayes answers. But if either of those conditions is not true, the two analysis methods can differ, sometimes substantially, and then we need to think harder about how to figure out which one is better than the other one. Yes, I did not address at all in this case study the issue of why I decided to get 400 patients worth of data rather than 4,000 or only 222 or whatever. People don't generally choose the sample size based on the idea of whether the resulting analysis will be better done from a Bayesian or a non-Bayesian point of view. People almost always choose the sample size based upon what their accuracy needs are in the study in question. And so I will try to work in a little unit toward the middle or end of the class on Bayesian sample size determination. Essentially, the simplest way to think about it is you can imagine at design time how narrow you need the posterior distribution to be to have a sufficiently narrow uncertainty band around the thing that you're trying to estimate that will allow you to make confident decisions, for example. And so you can work backwards from that to work out what sample size you need. That's a simple way to do it. And the complicated way involves decision theory. in which you actually try to quantify the costs to you as a scientist of having too little data and also of having too much data. And you try to find the sweet spot by maximizing expected utility between the two things to be avoided of not enough data and too much data. We're all familiar with the concept of not enough data, although many of us in Silicon Valley are working with very big data sets indeed, and we don't really necessarily feel that we don't have enough data. Even a data set that has millions of observations can be not enough data for some purposes, because you may turn out that the number of predictor variables that really creates that exchangeability grid I mentioned before for a data set in the millions could itself still be in the thousands. And when you think about that, meaning that there's only a few hundred observations potentially in each cell of that exchangeability grid, you don't have a big data set anymore. So it depends upon how complicated the surface, the response surface, explaining the relationship between y and the x's, how complicated that relationship is in terms of how many x's there are and how complicated the surface is. But certainly we're all familiar, at least before the era of opening up a data stream and just waiting a few days and having millions of observations from websites and so on. We're all familiar with the idea of having not enough data, and the problem there, of course, is that your uncertainty bands are too wide, and so you aren't able to make confident decisions about what needs to be done, or draw confident inferences about what the true state of nature is, for example. But why might it be true that you have too much data? I claim that can happen all the time. When data has an actual direct cost to gather, and again, in an era where we just have to set a web environment up and turn on the tap and wait, maybe the actual cost of collecting the data isn't very much. But suppose you were in a world, and not everybody in the room here comes from the tech industry where we're fiddling with web pages. Suppose you actually had to pay for the data. Then what would be the situation in which you had too much data in any sense? Well, there you go. That's one way to talk about it. What's your thought? That's right. Beyond a certain point, you have gotten enough data that you have uncertainty bands that are narrow enough that you can make a confident decision or you can make a confident inference. And in a situation where data costs you money, any data gathered after that is money wasted on this problem that should have been spent on the next problem you're working on, because we're all having to work on multiple problems at once. And we live as humans in a world of constrained time and money resources. And so it's always good to think of the arc of your entire career, so to speak, along with the working on the problem you're on now. There's very much such a thing as too much data for a particular problem. And the sweet spot between not enough data and too much data can be quantified using utility functions. And it's a complicated way to do Bayesian sample size determination, but it's the most satisfying way I've seen. I'll see if I have time to tell you guys about that. Okay. Let's see. Now, let's make a direct comparison with the Frequentis story. As I showed you before, in Mr. Neyman's world, on this page here, it says to analyze these data as a frequentist. I should have said to analyze these data as a frequentist operating in the Mr. Neyman mode rather than the Fisher mode, because we already analyzed the data from the Mr. Fisher point of view using the Likelihood function. And in fact, if I take you back to a slide in part 1, or maybe it was earlier in this part, so let's go back a goodly ways in this part here. You remember that at the end of this story here, back on page 14, we saw that Fisher's technology only provided us with 95% intervals that worked well when you had a lot of data. He was basically saying, I'm hoping that the sample size is large enough that you get a nice normal curve right here, and that therefore you can start at the MLE and go around 2 standard errors either way. And the standard error itself only works best, his approximate standard error based on Fisher information only works well in large samples also, because it's a large sample calculation. He did a Taylor approximation and left off some terms. And with small sample sizes, those extra terms that were left off actually matter. So his standard error isn't necessarily that good either. So Fisher's technology in small samples always produces perfectly symmetric intervals that may not have the right standard error connected with them, and when it's wrong, it'll tend to be a little smaller than it should be. And the fact that they're symmetric isn't always right either, because sometimes your uncertainty is deeply asymmetric about something. So Fisher gives us an approximate way to do things, but the approximation only works with large sample sizes. And he also doesn't say how big is big enough. He just says, if your n is large, then you can use this as an approximate 95% interval. So there's a lot of unanswered questions about Fisher's story in actual problems related to whether your n is big enough that he gets good answers. Here, because the central limit theorem happens and we get a likelihood function that is nice and close to Gaussian, here I wouldn't worry. Fisher's answers are going to come out pretty much the same as the Bayesian answers, and they're also going to come out pretty much the same as Mr. Neyman's answers as well. So you may recall Mr. Neyman's story was motivated quite differently than what we saw from Mr. Fisher, in which I had this rather busy diagram that we worked out last time, where I think about the population data set and the sample data set and the repeated sampling data set. And in order to get the relative frequency probability story up and running, I had to imagine not just getting one sample of size 400 that I think of as like a random sample and getting the mean of that sample to get my theta hat. I have to imagine getting many such samples and collect all of the theta hats together into a data set over here and then think about what its properties are. And so we ended up with a picture that looked like this. It was the density of the estimator theta hat, and you can ask yourself, where did Neyman's estimator theta hat come from? And he has a harder time answering that than Mr. Fisher does. Fisher says, well, I've told you already how to get a good estimate. Use the maximum likelihood estimate. So find your likelihood function, take its logarithm, and take the first derivative and set it equal to 0. That's your MLE. As long as things are nice and bowl-shaped down around the maximum, nothing bad can happen. Neyman is in a harder position because he doesn't want to use likelihood, because that was a Fisherian thing to do, and he and Fisher didn't get along very well. So Neyman is reduced to ad hocery. Neyman is reduced to saying, in this problem, you're interested in the population mean, so the sample mean should be a good estimate. That's sort of the level of Neyman's argument. I think the sample mean should be a good estimate of the population mean. And having chosen that particular estimator, then his diagram unfolds with respect to that estimator. So if here, instead of using the mean, we'd use some other summary of the ones and zeros, then his repeated sampling data set would be with some other summary of the data. In any case, he gets a data set over here in the repeated sampling story, and he can make a histogram or kernel density trace of it. And in large samples, he's hoping, by the central limit theorem, Neyman is also hoping that it'll look a lot like a normal curve, centered at the truth, and with a standard error that we got by making that calculation we did last time, which turns out to coincide with Fisher's standard error here. And then, as you remember, Neyman did this confidence trick where he wrote down a probability statement about theta hat and made it look like a probability statement about theta and got this interval. That turns out to coincide in this problem with Fisher's interval. So all three ways to skin this cat in this problem turn out to lead to substantially similar answers. So we're back here in the Bayesian world now. And so you would appeal to the central limit theorem. The repeated sampling distribution of the sample mean y bar you could hope is approximately normal. And you can use standard calculations to show that that distribution should be centered at the truth theta. And with that repeated sampling variance we worked out last time of theta times 1 minus theta over n. And so now, using Neyman's confidence interval idea, you start at the sample mean and go roughly 2 standard errors either way. And that runs from roughly 0.142 to roughly 0.218. And Fisher would get exactly the same thing. And by contrast, the posterior for theta is also approximately Gaussian. On the next page, I've plotted the actual posterior in solid versus the Gaussian approximation for it. In other words, I've superimposed on top of that the normal curve with the same mean and standard deviation as the posterior distribution here. And you can see, if you were being pedantic about it, the posterior is a little bit has a little bit of left skew in it. But okay, they're really close. And so why not just go ahead and use the normal distribution as an approximation for the Bayesian answer as well? So the posterior mean we saw was 0.178, pretty close to the 0.18 we would use from the frequency story. And the posterior standard deviation, we go ahead and stick in that stuff into that variance formula, and out comes the number 0.0184, which is slightly smaller than the Frequentis standard error, which was 0.0192. And why is that? Why does the Bayesian posterior standard deviation which acts like the Bayesian version of a frequentist standard error. Why is this number here a little smaller than that one? Pardon? That's right. This thing is based on 400 votes worth of data. This thing is based on 430 votes worth of data. And so it's going to be a slightly smaller posterior standard deviation. And then the 95%, as people call it, central posterior interval for theta would run from about start at the sample mean and go roughly 2 standard errors either way. 2 posterior standard deviations either way. And you get practically the same interval. Rounding to the 2 significant figures, which is all you should probably report in this problem anyway, both intervals run from 0.14 up to 0.22. Yes, using the logic of the updating here, the updating goes from alpha to alpha plus s. And so if you wanted the prior to have 0 information in it at all, what should you do to alpha and beta? Make them get close to what? If you wanted the right-hand side just to be driven by s and n minus s, and so the prior disappears completely. Put it another way, the prior sample size was alpha plus beta. If you wanted to have essentially no prior information coming in based on that formula, what would you use? Alpha and beta would be close to 0. And in fact, the uniform distribution has alpha and beta both equal to 1. And that's also very close to 0 when you're comparing it with an n of 400. So that's like prior 2 votes in the prior and 400 votes from the data. But if you wanted to go to the extreme, you could try to go down to alphas and betas that were close to 0.1 or 0.001 or things like that. And you're getting pretty close to an improper prior when you do that. The beta 0, 0 distribution is improper. There isn't that much in it in this problem, right? Because the sample size is big enough that these small things we do with the prior aren't going to have much effect on the posterior. But you could look for a prior that really had virtually no votes in it at all by letting alpha and beta get close to 0. And we'll see that tricks like that are possible in other problems as well. So here we have 2 different approaches, actually 3, frequentist Neyman and frequentist Fisher, and then Bayes, and all 3 of them essentially give pretty much identical answers in this problem. And as I said, that's a result that's typical of situations with 2 things, fairly large n and relatively diffuse prior information. Those are the 2 ingredients that make the likelihood story a good approximation to the Bayesian story. But there's a vast difference in the interpretation of the 2 approaches. And so I want to make sure that I get that into the notes as well. So the frequentist is thinking about the repeated sampling distribution, DIST for short, of what he or she thinks of as the random variable theta hat. And he or she finds in this problem that that's going to be like a normal curve by the frequentist version of the central limit theorem. So this is the frequentist talking here. Centered at the truth theta and with an estimated standard error of about 0.019. That's the frequentist story. The Bayesian story has us look at the posterior distribution for theta given y, and in this case here, relatively diffuse prior information. And this is also a normal curve by a Bayesian version of the central limit theorem. But instead of being centered at theta, this is a distribution for theta centered at theta hat, and with practically the same posterior standard deviation, about 0.018 roughly. I'll call it just approximately 0.019 also. They're just about identical. So if you look at that, they're actually telling 2 different stories, but the 2 different stories lead to the same numerical conclusions. So the frequentist person, and this is the Bayesian story down here, the frequentist person, in the frequentist story, you got your theta hat and your theta. To the frequentist, which one is fixed and which one is random? In the top picture there, theta hat is no. In the frequentist story, theta hat is random because it's the thing that has a distribution. And so theta hat is random, and theta is fixed. And so we're thinking about a world in which you could get different data sets, and your theta hats would vary randomly around the truth. That's the world of Mr. Neyman and Mr. Fisher. In the Bayesian story, it's exactly opposite to that. Theta hat is the thing that's fixed because it's based on the data, and you're only going to have one data set. It's sitting right in front of you right now. It's a fixed known number, theta hat. And theta is the thing that you don't know, and you're using the machinery of probability and random variables to quantify your uncertainty. So in some sense, you could think of theta acting like a random thing, and theta hat is a fixed thing. And both of them are normal curves. And so why do they get quantitatively the same results? Well, let's write down the frequentist normal curve. It's going to go some normalizing constant times e to the minus some other constant times theta hat minus theta squared. That's the frequentist one, because that's how normal curves look, right? And the other one, it's going to have exactly the same normal curve. It's going to go the same C1, e to the minus same C2, but it's going to go theta minus theta hat squared. And why do we get the same thing? Because the normal distribution is that extraordinarily rare distribution that is symmetric in its two arguments. If I showed you this formula, could you tell whether it is a normal distribution for theta hat centered at theta or a normal distribution for theta centered at theta hat? Can you tell just looking at the formula? You cannot. And because it's the same normal curve, but interpreted two different ways, when the sample size is large and the prior information is diffuse, you have to get the same answer both ways. And that sounds like a pretty easy thing to, I've just illustrated it to you in what I hope is a pretty easy way. It's actually got a famous name. It's called the Bernstein-von Mises theorem. And it just basically says, with a lot of data, as long as the number of parameters you're trying to estimate in parametric models remains fixed and the sample size gets really big, Bayesians and frequentists are going to get more or less the same thing. And the people who first worked that out were Bernstein, the guy for whom Bernstein polynomials are named, and von Mises, Richard von Mises, one of the guys who did a bunch of theory connected with the frequency story. So this is the Bernstein von Mises theorem. But it's just a kind of common sense thing that under certain conditions, you're going to get a similar answer in both paradigms, and therefore you might as well use the frequency story as a calculational approximation to the Bayes story. Now, and this means, among other things, you remember we've agreed already last time that it's not legitimate. Oh, I'm in the wrong place again. It's not legitimate with the frequentist approach to say the frequentist probability that theta lives between 0.14 and 0.22 is around 95%, because to a frequentist, that statement is absurd. Theta is just a fixed unknown number that either is between 0.14 and 0.22 or it's not. So that statement has no meaning. It's not approximately equal to 0.95. It's actually undefined in the frequency paradigm. And yet the corresponding Bayesian statement, the Bayesian probability that theta lives between 0.14 and 0.22, given the data set Y and diffuse prior information, that probability does make perfectly meaningful sense in the Bayesian approach and is equal approximately to 0.95. And so essentially what's going on here is that the very common practice that we see in science of people computing inferential summaries in a frequentist way and then interpreting them in a Bayesian way, there are conditions under which that's justified, namely diffuse prior information in large N. Yes. Yes. That's right. And so he said basically that the second of those two statements is a probability assessment of the uncertainty of anyone who has the same database and the same prior information as we do, having chosen by De Finetti's theorem to use the same sampling distribution. Whereas the frequentist thing, if it existed, would be an attempt to try to create some sort of repeated sampling style probability story about theta, and you can't do that because theta is just a number that isn't moving around. Whatever you imagine repeating theta is just all sitting there. And so, in fact, if you were ever a student in a statistics class taught from the frequentist way, and they had a question on the final exam that said, is that frequentist probability, that first one there, 95%, and they took 10 points off on your exam when you said it was true, you should write back to that instructor and get your 10 points back now, because actually it is true when you think about the probability from the other point of view. Or if you were ever a teacher and you inflicted that particular thing on students, you should contact them all and give them their 10 points back. Because, in fact, with diffuse prior information and large sample sizes, it's perfectly okay to calculate an interval estimate in a frequentist fashion and then reinterpret the interval in a Bayesian fashion. Now, when non-diffuse prior information is available and you go ahead and use it, then clearly by the logic of what we've seen here, your answer will differ from that of a frequentist analysis that's based on the same likelihood, because that person will in effect, and you can start to see where the two methods can create divergence. A frequentist analysis of the data set we just looked at is equivalent to a Bayesian analysis with what prior? In other words, if you were to take your likelihood function and reinterpret it Bayesianly, what prior would we have had to use to have the likelihood and the posterior match each other perfectly? The uniform prior. And so, looked at in that way, any frequentist analysis can generally be regarded as a Bayesian analysis with a particular prior distribution that the frequentist just didn't bother to say out loud. And actually, the problem with some frequentist analyses is that when you look at them in that way, the implied prior distribution is not very sensible, actually. And I'll give some examples of that later on. So, a way to think about these two approaches is that the Bayes story is perfectly general, and the frequency story is a special case of it, in which whenever someone does a frequency analysis, they're doing a Bayesian analysis with some kind of implicit prior that they didn't actually have to articulate. And if you back their analysis backwards, sort of reverse engineer it and figure out what the prior is that corresponds to that Bayesian analysis, sometimes it's a prior that the frequentist would not be very proud of. And those are situations when frequentist methods don't have very good repeated sampling characteristics. You don't always get 95% coverage of your intervals from the frequency story. That's something to bear in mind. However, when you have non-diffuse prior information and you use it, then you're going to get a different answer, and that different answer could either be better or worse than the answer that you got from the frequency story. And it's pretty clear how it's going to go. If your prior information is retrospectively seen by you and other people to have been well calibrated, to have been decently in step with the real world around us, then you're going to get a better answer than the pure frequentist answer. And if your prior, that's a strong one in this case, is retrospectively seen to have been out of step with reality, then you're going to get a worse answer. And it took me about 30 seconds to say that, and it wasn't very hard to think about the ideas that led to that 30-second statement. And yet these guys, Samaniego and Renault, got a JASA paper out of that, Journal of the American Statistical Association, one of the top journals in statistics. And the paper just basically says what I just said. And so you get a little box in which you can say, in effect, the frequentist analysis, which does not try to bring in prior information, the frequentist analysis with the same likelihood function operates in a position that's intermediate between a bad Bayesian analysis where someone has brought in strong prior information that's out of step with reality, and is worse than, the frequentist story is worse than a good Bayesian analysis where someone has brought in strong prior information that is well in step with reality. And if you were, there's a idea in decision theory called minimax, which says you're a person who goes around trying to minimize the worst thing that could happen to you on a moment-by-moment basis. You could look at that box there and say, well, I'm just going to be a frequentist all my life because I want to avoid being a bad Bayesian. And because I'm trying to be minimax, I'll just make sure that I never fall into the bad Bayesian box, and that will exclude me from the possibility of ever getting into the good Bayesian box, but I'm going to be minimax, so I'll go ahead and do the frequency thing. But if you've ever studied decision theory, minimax is a bad way to organize your life. Moreover, I'm going to show you in this course methods with great frequency, if I can use that word, with great frequency falling in the good Bayesian box across the problems that you work on. And so there are ways to consistently land in the good Bayesian box, and so why not try to go there instead of settling for the middle box. Now I want to take a moment and show you something from the course webpage. Actually, first I want to say this NB. Well, in fact, well, if you do both techniques, if your modeling makes a testable prediction in the world, and the frequentist model makes a prediction that's different from the Bayesian prediction, then we can wait a while and see what the world tells us. But a lot of people are doing inferences, and they never get to find out what the right answer is. And so all you can say in situations like that is that the frequency analysis differs from the Bayes analysis, and we can't tell which one is better because we don't know what the truth is. But that's the role of simulation studies. When I have a complicated data set and I'm not sure how to analyze it, a good thing that I always try to do is to create a simulation environment in which I create a whole bunch of other data sets that are similar to the one I have, and I try out different methods on them, except that in the simulation world, I know what the right answer is. I mess with the parameters I'm playing God, basically. I know what the right answer is, and I can find out which of the variety of methods I have does a better job of recovering known truth. So the simulation world is a place where we can actually find out which of those three boxes we've landed in. Other than that, it's pretty hard. That in the world where we do actually make testable predictions and see what went right and what went wrong. Later on, I'll give several examples in which a Bayesian analysis is better even with diffuse prior information, because it's going to turn out that the process of maximizing a likelihood function isn't always the best way to summarize it. In fact, I'll make a little sketch of that right now. Later on, we're going to have these things called variance components models in the part of components models. Can't spell today. Never could write, but today I can't spell either. These variances come about, and so you can get situations where the marginal likelihood for a particular variance parameter given the data set looks like this. Extremely skewed with a maximum at 0. So if you're Mr. Fisher, what's your maximum likelihood estimate for that parameter? 0, right? Maximize the likelihood function. So here, Fisher is going to say sigma hat squared MLE equals 0. And what happens in these models is that you can conclude that it's 0 when it really isn't, and that fact of it being 0 will propagate through to the other uncertainties that you have in the model in such a way that all of your intervals become narrower than they should be, in fact, substantially narrower than they should be. And so the problem is that that's a distribution that is very poorly summarized by its maximum. For every other purpose, if you gave this data set to people in statistics 1 and asked them, the entire data set lies to the right of 0, what would you use as a good summary of the center of it? The answer would be some number like the posterior mean, which is the balance point along the number line, or maybe the posterior median, which is a place sort of like that. And all of these things you could do instead if the posterior is like the likelihood function with a relatively diffuse prior. You just use summaries like that instead. And here's what happens. A cool thing happens, which shocked the frequentists when it was first pointed out to them. Here, in this problem here, you get better frequentist answers from the Bayesian approach than you do from the frequentist approach, because you're summarizing a heavily skewed likelihood function in a more intelligent way. You're summarizing it with something like a posterior mean rather than a likelihood mode. And the result is that you get better frequentist inferences from a Bayes procedure, because it does a better job of summarizing what's going on here. So a kind of principle that lots of frequentists have begun to adopt at the end of the 20th century and here at the beginning is the basic Bayesian idea of integrating over a likelihood function, which is what the Bayesian story says to do. Integrating over a likelihood function produces better frequentist answers than maximizing over it under some conditions. But sketch for me, please. Tell me how to sketch a different sort of posterior distribution in which it doesn't matter whether you integrate over or maximize over it. What's an example? A normal distribution. Suppose the likelihood function for this sigma squared given data looked like that. Then when the marginal posterior distribution is Gaussian, it doesn't matter whether you integrate over it or maximize over it, you get the same answer. So Fisher works great when the picture looks like that. Fisher works terribly when the picture looks like that. And the standard software for fitting variance components models does not print out this picture to show you whether you're in this world here or this one. It just gives you numbers based on maximum likelihood. And so lots of people around the world for decades now have been getting bad answers out of the likelihood story in situations like this because they don't have good diagnostics in the software. Anyway, I wanted to show you one other thing that's on the course web page, and that might take us to the moment when I have to rush for my car. Let's go back here to the course web page and look at what's going on David Leonhardt's story. In fact, I'll download it to the desktop because I can. Oh, thank you. Let's come back over here because I can then, where did he go? There it is. I can then go full page on it. I don't know, is that better or worse than what I had before? Maybe we can scroll. So this article was published in April 2001. And so when Leonhardt says about a decade ago, he means in the early 1990s. Some Scottish researchers in the mountainous Grampian region of Scotland, they ran a randomized controlled trial to assess the effectiveness of a new drug for trying to help people with heart attack. So these are people who already just had a heart attack, and they're trying to administer this drug to them in the ambulance on the way to the hospital. And this drug is called a clot buster, and the idea is that one of the things that can cause you to have a stroke or even die after a heart attack is when the heart attack process creates a blood clot that goes to your brain, for example, or goes to your lungs, or goes back into your heart and causes a second heart attack. You want to try to prevent those clots. And so they gave the people in the treatment group this clot-busting drug, and they gave the people in the control group the current best treatment other than that. And they published a paper in the British Medical Journal, one of the top two British medical outlets, in which they announced an astonishing finding. The drug had reduced the death rate of heart attack victims by about 50%. And in fact, what you find when you do medical research is that that's a kind of low-hanging fruit that is never there anymore. To do something that lowers the death rate by 50% is something like a miracle in medicine. That's just really amazing. And so there you have this article, and it was based on a relatively small sample size, only 300 patients in the treatment and control groups combined. There is reason to think maybe that might not be the best possible way to summarize the data. So my old friend, David Spiegelhalter, the guy who led the development team on the WinBug software we're going to use later on, working with his colleague Stuart Pocock, they didn't believe it. And so they set out to do the following. They wanted to use information external to the data set for this one drug to try to forecast what a meta-analysis by the medical literature 10 years into the future would say about the actual value of this drug. And by a meta-analysis, we'll talk about this later, I mean a study which takes as its data points other studies and combines them. And a meta-analysis, when it's done right, is meant to be the definitive summary of what medicine knows about this particular treatment. So Pocock and Spiegelhalter set themselves the task of trying to use information external to this Scottish study to predict what the meta-analysis would conclude 10 years into the future. And to do that, they had to construct a strong prior, because the only way you're going to get an answer that's different from this answer here is to use rather strong prior information. And here's how they built their prior. They said to themselves, well, this is the only time anyone has ever actually created a study of this particular drug. I'll buy that. But there are many other studies of other clot-busting drugs with similar chemical signatures. And so they built a prior in which they drew information hierarchically in a way that I'll show you how to do later this course. They drew information hierarchically from the other studies of other similar clot-busting drugs. And they did it in a way that was properly skeptical about how those other drugs are not identical to this one, but you would expect them to be similar to this one. And they ended up with quite a strong prior, and they combined it with the data from the Grampian study and announced the finding. They weren't just doing this for their health. They wrote a letter to the BMJ, the British Medical Journal, shortly after this study was published, in which they predicted what the meta-analysis 10 years into the future would conclude about this drug. And the answer is on the next page of the little article here. They predicted that it would be believed 10 years in the future, after a good meta-analysis had been done of this drug, that in fact the mortality would be reduced by this drug down by 27%, not 50%. And now they have made a testable prediction. They have said, we think that 10 years from now, the medical literature is going to think that this drug's actual effect is closer to 27% than it is to 50%. And now all we have to do is wait. And this is what Leonhardt did. It's still a big improvement, yes, definitely. You look around in medicine for 5% improvements when you can find them, and you're delighted when you find a 10% improvement. So now we wait 10 years, and now the meta-analysis comes along, and whoops, I didn't mean to page down, I meant to go down like this. And another top journal, the Journal of the American Medical Association, published about 10 years later a meta-analysis, and it showed that, in fact, the drug reduces death by about 17%. And so what's happened here is that this is a case where these two Bayesian investigators, Spiegelhalter and Pocock, had the scientific courage to use strong prior information that was based upon a similarity judgment. It's almost like in one of these exchangeability judgments we talked about. They said to themselves, we think that the Grampian study should not stand alone. In fact, we know quite a bit about this drug because its chemical signature is similar to that of other clot-busting drugs. And so we believe that we will find later on that the right effect of this drug is closer to 27% than 50%. And the right answer, when they waited 10 years to find out what everybody found from many, many studies, was 17%. So here's an example where a Bayesian analysis with strong prior has come up with a far better answer than a Frequentis analysis that didn't use that extra information. And the Grampian people could have done this, you know. They could have published a paper in the BMJ in which they combined information from their study with the relevant information from the other studies that are similar clotbusters, and then they would have not have been in the position of overstating their findings. The Frequentist approach has the disadvantage that it encourages us to think of each study as a one-off rather than as part of a continuum. The Bayesian story is constantly saying, this is your uncertainty now, new information comes in, sequentially update. And so you're always trying to incorporate and build upon what came before. And the Frequentist story for a long time has had the unfortunate effect of making people think about their studies one by one. And when you publish papers like this one by one, you get outliers. You get answers in them that aren't as good as they could be when you brought in the extra information. So this is an example of people who brought in strong prior information and ended up with an answer that was substantially better than what the people got who just simply reported Frequentist findings on that one study. And I think that draws us to a close for this week because I do have to go run to get that meeting. So I offer you, as I said, a chance to do some readings from those books if you get copies of them, and to write to me if you have any questions. Please also start working on those problems if you want to do some things along those lines, and you'll find the solutions to be quite helpful, I hope. Again, I'm available to you if you would like to ask questions about those problem sets as well. And we will be, as I said, not meeting a week from today because there wasn't a room available, but we will be meeting 2 weeks from today. And my intent is to have that meeting last for the whole 9 to 5 schedule. I may have another day or so along the way where there's another unavoidable meeting at UCSC, but I hope not. So thanks for coming again, and I'll see you in 2 weeks. So that finishes the video, guys. That finishes the taping for today. Thank you very much.